today we're going to demonstrate what is a quarter wavelength antenna and what is a half wavelength antenna from the EMC perspective. Okay, so we are going to look at a cable structure which could act as an antenna, and we're going to look at it from the frequency domain this time. As you can see, our demonstration setup is here. We have a spectral analyzer with tracking generator function, signals getting out of the tracking generator output, and through this T connector, we have some signals received from the input. And at this port, we are going to connect a coaxial cable. Okay, so this will be our antenna structure or resonance structure on the discussion. Okay, so we are going to look at a differential mode first, and then to look at the common mode, which is more relevant from the EMC perspective. So if I start drawing this simplified setup, we have a signal source coming from the tracking generator, and often it has a 50 ohm source impedance. And in this case, we're going to connect a coaxial cable. I draw like that, so that's my coaxial cable. We're going to look at the resonance frequency and how it is related to the length of the cable. Okay, so we can definitely measure the length of this cable. And we have two coaxial cables with different lengths. Okay, so the first one, let's have a look. It's about 40 centimeters. Okay, so the first one is 40 centimeters long, and the second one is about 80 centimeters long. Okay, so twice the size as the shorter coaxial cable. Okay, now before we connect this coaxial cable to the port, I wanted to explain. So this is what we measure 40 centimeter, and this is what we call physical length. And we know that when we send signals or power using a cable structure like this, really is wave action inside this coaxial cable. And the wave, we said, travels close to the speed of light. But because, in this case, the way we build this coaxial cable, the relative permittivity and permeability determines the velocity of propagation, and that velocity of propagation, we call it VP, is slower than the speed of light. So often, as a rule of thumb, I give it 0.7 to 0.8 as a ratio. Okay, so we know that the wave action inside this transmission line is actually slower than the speed of light traveling in free space. Okay, so that makes sense. Or you can view it as from another angle, because you can say, well, since my velocity of propagation is slower, then my electrical length, right? There's a term called electrical length, is actually longer than my physical length of the cable. So in this case, the electrical length of this coaxial cable is probably longer than 40 centimeters. Really depends on how you see it. Okay, so let's connect this shorter coaxial cable to the port first. As you can see, we have an open circuit coaxial cable here first. Okay, so we're gonna look at an open circuit coaxial cable. I can draw it in a transmission line manner, which I often use two bars to represent a transmission line. In this case, my transmission line is a 50 ohm transmission line. I have a 50 ohm input impedance, and here I have my open circuit. And from the transmission line theory, we know that when you send signals, right, at different frequency, you will end up with certain frequency of the signals, right? You will have what we call voltage standing wave. Okay, so I can draw like this. So this will be my voltage waveform that I measure. So this is if I have a imaginary voltage meter and I move inside the transmission line, and I will have the peak, we call it this point peak, and nulls, right? So my voltage will be doubling and almost zero, doubling, almost zero, depends on frequency. and this is based on an open circuit transmission line. Okay, so yeah, let's have a look. Okay, so now I can connect this to this test setup. Okay, so you can see that we have some resonance behavior observed in a spectrum analyzer. Okay, the marker 2 and marker 3 really are the third and fifth harmonics of the first frequency point, which is the fundamental frequency, or we call the resonance frequency of this cable. Okay, so in this case, the resonance frequency is about 117.3 megahertz. We know the physical length is 40 centimeters. We know the velocity of propagation, and let's check if the math matches with what we measured here. Okay, 117 megahertz, and it gives us a quarter wavelength of 0.45 meters. It's like 45 centimeters. Not far off from what we've seen here, right? Not far off from what we measured here. So that makes sense. Okay, so we proved that this 40 centimeter long coaxial cable would have a fundamental resonance frequency at 117.3 megahertz. But we know that this is a open circuit, right? Open circuit coaxial cable. If you have a short circuit, what happens is, for short circuits, you just have a shifted voltage standing waveform like this. Okay, so what was peak now becomes null, and what was null becomes peak. That's it. Okay, so to demonstrate that, I can go to trace and fix this view, and then I can just connect a short connection to this, and then you will see what I mean. Okay, so now this is a short coaxial cable, and we also know from the discussion that if we have a 50 ohm termination, okay, 50 ohm termination, we shouldn't see any resonance because it is a matched transmission line. And see, now 50 ohm, it is matched, so there's no resonance in this coaxial cable. So that's from the signal integrity point of view, that's something we want, and also from EMC point of view, maybe that's also something we want. But bear in mind, all this discussion is inside the coaxial cable, so we can treat it as a differential mode here. But most of the cases, as we know, you probably won't have an open circuit. You probably won't have a short circuit, and you will most likely will never have a 50 ohm termination. So let's have a look. For example, if I put two more 50 ohm feed through here, so that will give me about 16 ohms, right, as a load. Let's have a look what happens. So this is my 16 ohms termination. You can see you will have some resonance, but it is not as obvious as a open circuit or short circuit. Okay, so this is an unmatched termination, so you can see that. And we demonstrate short, open, and matched termination of this short coaxial cable. Now let's have a look at this long coaxial cable. So again, I'm going to just do an open circuit so we can have a comparison. So now I remove this short coaxial cable. I'm just going to connect open circuit again, because we know, roughly speaking, the length of this coaxial cable doubles the length of this coaxial cable. And as will be measured here, right, when you double the length of the cable, you half of the resonance frequency, as demonstrated here. So if you look at trace 2 now, the resonance frequency actually becomes half of the shorter cable run. Okay, so that's everything we demonstrate here is very basics. Is transmission line theory. If you go to university, you studied transmission line theory, you will find this is easy bit. Okay, now as I said, all these discussions so far is within the transmission line, right? What happens inside this coaxial cable. Now let's move to the next subject, which is to look at the common mode structure, common mode cable structure, because that is often the root cause of radiated emission, and see in reality how this, what we discuss here, this quarter wavelength antenna behavior would affect the radiated emission in a more realistic scenario. Okay, let's move on to that. So now we're moving to the common mode demonstration. First, we're going to have a look at the half wavelength antenna. So if I'm a radio guy, radio amateur, and I say, okay, I want to make this coaxial cable to be an effective antenna, right? I want to use it to transmit signals to the maximum as far as I can, as effective as I can. What can I do, right? Given only I have one coaxial cable here. An obvious way of doing it is I can feed signal at the center point of this coaxial cable. Because if you look at the common mode impedance of this cable, whereas this end and this end, they are open circuits, right? When I say open circuit, is they are really having a very big impedance compared to a common ground. And this common ground could be the earth, well, in this case, you know, it's a wooden table, but actually the earth I'm standing at or sitting on. So these are high impedance to earth, these are high impedance to earth. But the middle point, the feeding point I wanted to feed signals, actually has a relatively small impedance to earth. So often this value is about 70 ohm, 80 ohm-ish, okay? So if I want to feed signals, obviously I want to choose a low impedance point to feed signals. So this would be my feeding point, okay? So then I can make this coaxial cable as a efficient half wavelength antenna. To demonstrate that, right, again, I have very similar setup, and in this case, I have two current probes. We've used this a lot in our previous demonstrations. So these are matched current probes, and in this case, I'm using this one as a signal source and this one as a signal receiver, okay? So what happens is, if I do this, right? So what happens is, by what we call magnetic field coupling, right? Because the way this current probe works is really by magnetic field coupling. So I can also use it to inject signals, right? So these signals getting into the RF current probe will be coupled predominantly by magnetic field coupling to this cable. So it is as if I inject signals to this center point. And I have this current probe measuring the level of current at this point in the same time. So by doing this, I can see at which frequency I can have most current and at which frequency I have the least current. So that will represent a resonance structure as we explained, okay? So now if I turn on, you can see very clearly, right? At this point, which frequency is this? At about 142 megahertz, I picked up lots of current, right, via this current probe. Whereas if you go to this point, which is 313 megahertz, I picked relatively small level of current, and then this repeats again. And if you measure, because we know that the length of this cable is about 80 centimeters long, and then you can translate that into a half wavelength antenna, and then you will see actually the resonant frequency of this half wavelength antenna is 144 megahertz, okay? Next, you may ask, well, you know, this is really like, as you said, this end is like having a very high impedance to earth or ground, depends on where you reference to, and same with this. So in our product design, there's never going to be a case where these two having a high impedance to earth or ground. Often this end is connected to a a chassis or connected to a enclosure represents a relatively low impedance to earth or low impedance to ground, and perhaps the same with this end. So how is that going to affect us? So the next demonstration is to demonstrate that, okay? To start with that, as I said, this is a wooden table, so it would not be the best example to demonstrate that. So let's replace this with a ground. Now we have a common ground, let's call it, or we call it common ground or common RF reference. So this is often, when we refer to different grounds, Earth, and let's call this as our common ground for this demonstration, okay? So let's say if I have a equipment, in this case it's a oscilloscope, but it could be anything like a laptop or whatever, right? And this thing could be, in this case it's plastic, so it's just lay on this common ground. So most of the coupling would be by parasitic capacitance between whatever circuitry in this oscilloscope to this common ground. But often if you have a metal enclosure, you can bond the enclosure directly to a common ground. So that's even better to achieve a very low impedance bonding to this common ground. So now let's have a look. If I connect the same coaxial cable from previous demonstration, and I just connect it to this point. And this is a dummy unit. It's not powered. It just provides a relatively low impedance to this common ground now. Again, I'm going to inject noise from this probe, and you can really treat this. Let's say you imagine this is a unit, and you will inevitably have some common mode noise, right? And this represents the common mode noise getting out of the system and traveling on this cable structure, right? So now let's have a look how this antenna behaves. And now to demonstrate that, I put a insulation foam here, and I just put this end on this, right, on this bit, okay? So same. I'm gonna using this probe to measure the RF current next to it, and let's see what happens. We shift the resonance frequency, didn't we? So now if you look at, so previously we know it's about 144 megahertz as, if we inject signals at the center of the cable as a half wavelength antenna. But now, because we are providing a lower impedance at this end, and we inject a noise on this end, this cable all of a sudden becomes more like a quarter wavelength antenna now. So if you look at that frequency, resonance frequency, it becomes 86 megahertz. So more represents this cable now acts more like a quarter wavelength antenna, okay? But the point I wanted to make is really depends how you terminate the cable, right? As relative to a common ground or common reference, you will have different resonance structure. Now next, let's have a look, because this one is still, you can arguably say this has a high impedance to this common ground. What if we also provide a low impedance common ground to this? Let's have a look. See that changing again, and you can see because I'm just putting this on this common ground, and so it's not a really good connection, but you can already see we shift the resonance frequency again, because now this has a lower impedance and this also has a lower impedance to this common reference. Perhaps this gives you a better idea. Now, as you can see in this case, this represents a relatively lower impedance to the common reference. This end of the coaxial cable again perhaps represents a lower impedance to the common ground, and as you can see, we again shifted the resonance frequency. Okay, I mean, we can do a lot to try to characterize and calculate this kind of resonance frequency, but perhaps the most important point taken from this demonstration is that a cable depends on how you connect it from the common mode point of view, right? It could be low impedance, high impedance, or low high or high low. Then your cable would behave differently. Sometimes could be a half wavelength antenna, becomes a quarter wavelength antenna. And again, depends on the noise source, the frequency of the noise, it will radiate very differently. So hopefully this is a very simple demonstration and then give you an insight of how cable behaves in a typical system installation. Okay.